Peter,
Great to have you here.
well, nice to be here. I've actually visited you, I know, in the past. But it's nice to have Peter back in New Orleans. It was also very nice to have him as a PhD student. He was just a great person to work with. So Mark and Peter asked me to come and talk about what I've been up to. So I thought that meant probably something to do with my research. So there is a project that I'm part of about relevant to quantum computing that involves a number of universities. And the role that Tulane's been playing in this is to develop models for quantum programming languages that support recursion. So I want to tell you some about that and about the work at Tulane. It's joint work with Bert Lindenhovius, who is postdoc, is still at Tulane, and Vladimir Zamdzhiev, who was a postdoc with me for 3 years and then defected to Eastern France, where he's now working on the ZX calculus. But he still participates in this project and has been a very important figure in it. Okay, so what I want to do is start by thinking about what is a quantum computer, and we'll adopt Nil's QRAM model, which says a quantum computer ought to be a classical computer with a quantum coprocessor. And the connection between the two is that on the classical computer you can create, build circuits, quantum circuits that you send to the quantum coprocessor, which executes them, and then you get in return measurements to tell you what the outcomes are. And here for us, a circuit is simply a sequence of unitary operators. Some people add the measurement in as part of it, but let's just leave it there. And in fact, the issue we were first confronted with is how do you program such a device? So to talk about that, I thought it would be useful because this gets very technical mathematically. I thought I would do some background in logic and math as preparation for you. We'll end up in some weeds, but hopefully the stuff I do at the start will be enough to maybe even get you interested in looking a little deeper. If I just dove into the results, I'd lose you right away. Maybe I've lost some of you already, but we'll see. Okay, so some basics. I thought I'd start at the very basics with logical foundations. So if you start with the predicate calculus, this is something I think everybody sees at some point, I hope, where you have predicate symbols, function symbols. Each of these come with a fixed arity telling you how many inputs they expect. And then you can write terms that consist of variables, constants, and a function symbol of n variables. You enumerate which n it should be that it's expecting. And now you can write formulas in this logic that look like a predicate with some number of inputs. You can interpret this perp symbol as bottom, as false, and t is true, and then you have negation, conjunction, disjunction, implication, and then the existential, the universal and existential quantifiers. And this logic is one of the first things you prove if you go into the depths of it. It's sound and complete. If you can prove something's true in the logic, then it's true in every model and vice versa. And models here just simply mean putting in truth values and seeing what you get out. So the next step up is to go to set theory, where you can, in particular, use the standard Zermelo-Fraenkel axioms, which includes the axiom of infinity, which says there exists a set which has the empty set as a member, and whenever it has some member, member T, then that set T union the singleton T is also an S, and that's the axiom that drives piano arithmetic, for example. This theory is sound, and it's semantically complete, meaning you have this equivalence with semantic models and proof in the system. But Gödel's amazing result in the early 30s was any system powerful enough to do arithmetic, and this one is incapable of proving its own consistency. Okay, so you can't prove that syntactically it's complete, which means either you have P or you have not P. It has to be true. That was a startling result at the time, and still is in a sense. This is one of the major accomplishments of the 20th century. But in return, one way to do things is to avoid the problem. And even in 1907, E.J. Brouwer was looking at intuitionistic logic where you don't include this law of the excluded middle, or equivalently that not A implies A. And the emphasis here is on proof, not validity, on what you can prove, not this semantic or the syntactic validity of things. And it turns out this is the logic of classical computation, as we'll see. Okay. In 1987, Jean-Yves Girard proposed something he called linear logic. And his motivation was try to get at more of the foundations of logic, or what he, or some people called at the time, the logic behind logic. And the idea there was, if you look at the usual rules in logic, if you have a hypothesis you use, you can duplicate it and use it again. Or if you have a hypothesis that you've used twice, you can collapse that use to just one use. So these are respectively called weakening and contraction. And he eliminated those and tried to develop a logical formalism that regards these formulas, these hypotheses, as resources. And he wanted to account carefully for how they were used in proofs. Okay? Now, that should sound familiar in a sense, because in computation you want to do that as well. You want to think about the resources. And this is the real interest in the community at the time, was among computer scientists, theoretical computer scientists, of using this as a way to get a real handle in theoretical computer science on how computations, what the cost of computation was. It was a sort of abstract way to deal with that. And derivations in this system that he devised that obey this paradigm of being used once and only once are called linear. And it turns out that, as we'll see, this turns out to be a logic for reasoning about computing over quantum systems where you have qubits, and you can use them, but you can't throw them away and you can't duplicate them. There are no cloning and no discarding results. Really are what this logic captures in an abstract way. And this is, in fact, I think the reason why I'm going through a lot of this is because without understanding this, you're not going to understand any of the models. Okay? So, all right. Okay, so what about computational structures? I've talked about the logical underpinnings. The computational structures started in 1934 with Church's lambda calculus, the untyped or unityped version, where you're just given terms where you have a variable, abstraction on a variable in a term, which is, think of, make the term, instead of a polynomial, a function of the variable you've abstracted on. So if t is a term, lambda x dot t is regarded as a function whose variable you're using is x. And then you can apply one term to another. So grammarians love to repeat the same thing twice and have you parse, what does that mean? You're not repeating t, this is a symbolic representation of two different terms that you apply one to the other. And there's some conversion rules that say, well, if you have an abstraction, is what this is called, with variable e, you can change the variable as long as the variable y is not one of the free variables in e. Free means not bound by some lambda operator. And then you have the beta reduction rule, which says if you have an abstraction and you want to apply it, so you want to substitute e prime for x, you can do that, and as long as the free variables in e prime don't intersect the bound variables of e. So you have this problem about clashing, capturing variables that are already bound when you apply terms. This calculus is Turing complete. What that means is that anything you can do with a Turing machine, you can do with this. This was a result of Turing and Church actually independently in the mid-30s. The functions you can encode in Turing machines are exactly the functions you can realize in this lambda calculus. And this, since it's Turing complete, it supports full recursion. Typically, the unwinding rule for a recursion says if you want to do rec x dot t, What that means is you, in fact, substitute recx dot t for x in the body t and see what you get. Okay? And if you read this, you realize that what this rule is telling you is that this term recx dot t is a fixed point of t. You apply t to recx dot t applied to, and substitute for x, you get recx dot t back out. And the reason that this calculus supports this, gives you this full recursion, is what's called a paradoxical combinator. This term in the calculus, actually, if you input any term t, you will get a fixed point for the t out of it. And that's how you get a recx dot t out of the t. Okay? All right, is this, okay, and then you can interrupt me with questions if you have them. If not, I'll just carry on. All right. All right. So that was the untyped version where you don't have an enumeration of any type structure. And it's very powerful. It gives you full recursion, for example, and it's Turing complete. There's another version that people like to study, which is called the simply typed lambda calculus, which is lambda with this arrow on it. And that's a calculus where you do enumerate some types. You have the unit type, which has one element in it. You have the integers, the booleans, and then the one combinator you use is the arrow type. You can have a type of functions or terms that map from taw to taw or taw to taw prime, if you like, if you want to be really careful about it. And the terms in this calculus can be variables, a null term, which is the only term of type unit, n for an integer, true and false for Boolean, and you have application, and then you again have abstraction, but now you see that this abstraction requires you to tell you what the type of the variable is. Now, the types were actually invented in set theory as a way to avoid paradoxes. And as someone once said, I'm not sure who, but a long time ago, they're meant to keep you from doing bad things. And so if you can invent an approach that keeps you out of paradoxes, like Russell's paradox, you have a set of all sets and there's a problem with that, then it's a good thing. And the computing community has adopted this quite strongly because it really helps with getting things right with programming languages. And then along with these types, there are what are called type judgments. So here's a judgment. So the horizontal line is meant to indicate the hypothesis you need to make the judgment on the bottom line. The gammas that are listed here, what those are they're partial functions from the set of variables to types. Partial, in fact, means in this setting that gamma has a finite domain. There's a finite set of variables where gamma is defined, and we can see in this rule, for example, what that's really saying. If x is a variable and you apply x and you get type taw, that's the value you get out, then you can make the judgment that gamma implies x has type taw. Okay? So on these lines, I don't need any hypothesis because each of these are constants. This is a null, this is an n of the type integer, true and false are both type Boolean. Here you begin to see how you put these together. I just talked about this one. Here we have, if you have a function type, an arrow type, gamma tells you that e has type taw, arrow taw prime, and e prime has type taw, then you can apply e to e prime and get something out of type taw prime. So that's application. And here's how you do abstraction. If gamma together with the knowledge that x is of type taw tells you e is of type taw prime, then gamma will prove to you that, or validate that, lambda x of type taw at e will give you a morphism or a mapping from taw to taw prime. Okay?
What exactly is gamma here?
Gamma is what's called a context.
Okay.
And so what it is it's an assignment to a finite set of variables, to types. Okay? And they're the things you need to make type judgments. Okay? So anything you do with types, you have to have an assignment of some variables that are mentioned in the terms. each of the terms that you want to make a conclusion about, like this or this or this, has some variables mentioned. And the role of gamma is to tell you what the type assignments are to the variables. Okay? And this just says that, this is the most illustrative one in this. It says if gamma is a partial function, x is in its domain and produces type tau as the value, okay? Then you can conclude that under this type judgment, that gamma tells you that x has type tau, okay? And then the other rules are just how you use the application and abstraction rules to make judgments. Okay? Is this?
Yeah.
Okay. If you know if you know types in programming language, I guess you know. So that's not going to help. This is exactly what you do in programming languages as well. You need context to put. If you want to run a program and it has some variables, you need to tell what values those variables ought to take on. Well, think of this as trying to run programs or evaluate functions or evaluate terms in a calculus. You need to know what values those terms take on, and the role of gamma is to tell you what the values of the variables you see are in that in that setting. And so gamma is called the context. It tells you what types the variables have. And of course, only when you have valid typing can you make the conclusions. Okay? All right. So, okay. So should I move on? Or? Okay, so in this simply typed lambda calculus, one of the most important results is the Curry-Howard correspondence, which says if you look at the intuitionistic propositional fragment of I'm drawing a brain freeze right now. Of intuitionistic logic, the propositional fragment of it, and use natural deduction as your proof system, then there's a nice correspondence with the simply typed lambda calculus. So over here we have a particular logic we're looking at, intuitionistic propositional logic. We have a proof system, which is the natural deduction system that you may or may not have seen. It's what's been illustrated in some of these rules, like these could be thought of as natural deduction rules. Then the propositions in this logic are in one-to-one correspondence with the types of the simply typed lambda calculus. And the proofs that you generate in this logic using natural deduction are in one-to-one correspondence with the terms. So this is a propositions as types paradigm. But what it's telling you is that intuitionistic logic is the logic of classical computation. It takes propositions to types, and the proofs are represented by the terms. Okay? So that's what classical logic can be viewed as, and that's a really fundamental result. Okay? Okay, well, there's also a linear lambda calculus. I told you about linear logic, and here you have a number of types. The null type, the zero type, sums, the unit type, a tensor product and not a Cartesian product. So this unit is a identity for the tensor product. There's a linear function type, and then there's this exclamation point, which is often called bang or of course. And what it says is it allows you to duplicate a term to make multiple instances of it. And so this is like telling yourself, instead of having one qubit, if I have bang of qubit, that means I have a resource for generating qubits. I'm not generating the same one over and over again. I've just got a resource for generating. Okay? Is that all right? So this is not it's not duplicating the same one. It's telling you you have a nice little family of them you can keep drawing on.
It's not cloning.
No, it's not cloning. That's the point. Yeah, but it's making available a source of them. Even in this linear world where you have to keep track of each one, this tells you I can in fact take bang of A, and I have lots of copies of A. Copies in a sense, they're each different instances, but I get to use them. Okay, so if A is qubit, I have lots of qubits I can use. No two of them I don't claim they're the same, but and I have to keep track of each one in the logic. And then the terms, well, they become much more complicated. You see things left and right and case, and this is all to deal with these constructors here. This is the inhabitant of the zero type, and so on. And down here on the bottom, you see pairs here. This is the inhabitant of the unit type, and you have pairs. And here you see a little change in the syntax where instead of writing lambda x colon a to say x has type A, we write it now as an exponent. It makes it a little easier to read. And you still have application. Lifting is a syntactic form of just this operation of making something duplicable, and forcing is the reverse. If you have something that you can have lots of copies of, like qubit, bang of qubit, I want to get a qubit out. Well, I use force to do that. Okay, that's what I'm doing. Okay? Okay, so if you have a system like this, you have the syntax where you can generate things, and then you have the semantics, which means you're going to have to define meanings to these terms. The goal is find a rigorous system in which you can define the semantics where you can use the proof theory of that system to validate properties of what you're reasoning about. And the most natural place to look for that is mathematics, because there's a very rigorous and I don't know how well understood it is, but we think it is, proof theory there about what you can prove and what's true and so on. So the idea here is, if I want to think about these systems, I want to find a way to map them into mathematical structures that reflect the structure that I'm looking at, where I can use mathematical theorems to prove properties of it. Okay? So in this world, we need what are called categories. So how many of you have even heard of a category?
Never heard.
You?
I've
Yeah.
heard that.
Okay, well then you can give this lecture. Okay, all right, so I wasn't sure who knew anything about categories. So I have some basic ideas here. I don't have them all, but okay, we'll see how it goes. So first of all, a category consists of a family of objects, and for each pair of objects, a family of what are called morphisms. They're the mappings in the category, the functions from A to B in the category. And there's a couple of rules you need. You need associativity. If you have a morphism from B to C and a morphism from A to B, then you can compose them. This composed with that gives you a morphism from A to C. And it has to be an associative operation, so you need three terms there, but I didn't write that out. And for every A and B, you have an identity morphism for every A. And that identity has the property when you compose on either side with the identity, either of the codomain or the domain, as they're called, you get F back again. There's an F missing there as well. So for example, the prototypical example is just the category of sets and functions. The objects are just sets, the morphisms between two sets of functions. And this just validates what you think about. Important in this work is the notion of what's called the Cartesian closed category. So this has to have finite products. If you get two objects, you can form the product type. So we can form the Cartesian product of two sets. There has to be a terminal object, so that means that's an object where every object A has exactly one map from A into terminal. And the terminal object in set is the one-point set. Okay? You can only have every set has a unique map into the one-point set, sending everything in the set to that one point. And there's what's called an internal HOM, which is denoted this way. So this is an object in the category. So this is an object of C, but it satisfies this interesting property, and it's miswritten here. So is there there's no markers.
Let me try getting one from next door.
Okay.
You want a whiteboard marker?
Yeah, I just want to, so I can write the formula correctly. So what it's telling you is if you have a morphism, a map from A cross B to C, you can what's called curry it and write it first iteratively as a morphism of A, a function of the first variable, and then from that you get a function of the second to the third. So what I should really have written here is the internal HOM from B to C. Okay? And that's called currying, and going backwards to one that has two variable inputs gives one output. That's called uncurrying. And set has this property where the internal HOM is just a set of maps between two sets. Okay, whenever Peter comes back, I'll come back to this. But is there any question about this? Do you understand what I'm trying to tell you here? Yeah? Okay. Mark says he does. I'll move on. Okay. Okay. What's this got to do with what we're looking at? Well, Lambics Theorem is that there's a one-to-one correspondence between Cartesian closed categories and models of the typed lambda calculus. I gave you the simply typed lambda calculus. There are other versions where you can have other typing rules, other types added, and each one of those corresponds to a Cartesian closed category, and every Cartesian closed category has an internal typed lambda calculus that sits inside it, and it is the type of the model for that particular calculus. Let me. Okay. Yeah.
Start with this,
Okay.
and then we'll use the whole plethora.
Okay. So I want to say C of A cross B, and this is a block C, is naturally isomorphic to C of A, the internal HOM from B to C. So what this is telling you is if you have A cross B to C as a morphism here, you can regard this as a function f sub x from A to a function from B to C. Okay? Where f sub x of any A puts A in as the first component of x. So this says f is a function, so f of xy is what you expect. And this says instantiate the first variable. If you instantiate this variable with, say, something called A, so let me say write this as f sub A. F sub A blank, that's f sub A. And that's a mapping that sends an element A to this map, which is a map from B to C. Because all I have to do now is, well, now that I've put in the first variable, I now only have to put in the second variable. And this operation is called currying the function to make it iteratively a function of the first variable and then a function of the second variable. And we use that a lot because it makes reasoning about multivariable functions easy as a sequentially a variable at a time. Okay? Is this okay? All right. Okay, so again, as I was saying, Lambics theorem says there's a one-to-one correspondence between Cartesian closed categories and models of the untyped lambda calculus. So these are the models you would be looking for. And this was the classical computation that we're interested in. Scott's corollary, this is Dana Scott, who was the first one to discover models of the untyped lambda calculus. What his corollary says is there's a one-to-one correspondence between reflexive objects. So what do I mean by this? Well, here you see an internal HOM of x to x. So that means the maps from x to x. And to say this means that this is a retract in x. So there's an embedding of this into x, and there's a projection that goes back so that if I embed and come back, I get the identity map. Now, you can always do this with just the trivial one-point space, okay, because there's only one map from the one-point space to itself. That's called the degenerate example, and it's of zero interest. To get a non-degenerate example of this is the interesting bit, where there's more than one element, and Dana's achievement in the late 1960s was to show there was such an example, and it's this so-called D-infinity model. I'll talk a little more about that in a little while. But in fact, what he got was one where, in fact, instead of just being a retract, it's isomorphic to its own function space. And what his corollary states is that the reflexive objects in Cartesian closed categories, so objects satisfying this property that the internal HOM from them to themselves is a retract of themselves, these are exactly the models of the untyped lambda calculus. Okay? So the takeaway here, and in fact, well, okay, so one point here is the only known non-degenerate reflexive objects in Cartesian closed categories are in domains. It's the only place you find in whatever domains are I'll talk about them in a minute. But the takeaway here is that the place to look for the semantic models for the classical programming languages, functional programming languages, is in Cartesian closed categories. If you've got a typed version, you want to look at a Cartesian closed category. If you've got this untyped version with full recursion, then you want to look for a reflexive object to model the calculus you're looking at. Okay? All right. So the next question is, well, this is all fine and good, but what does this have to do with quantum computing? Well, there's some recent work, well, what is it, 2019, so in the early 2000s, 2004, I think, was when this worked, and the years before that as well. So the common view is the Hilbert space formalism provides the basic model of quantum mechanics. Everybody believes that's where we work. Okay. Let's look at the category of finite dimensional Hilbert spaces. So I can think of this as sort of a finitary quantum mechanics world that I'm looking at. And linear maps. And it has a number of important properties. It has a symmetric tensor product. Symmetric means I can reverse the order. I don't get the same thing. It's isomorphic, right? If you take H tensor K, that's not equal to K tensor H. There's an isomorphism. It has a unit. If you tensor with the complex numbers with H, you just get H back again. You've got a zero object, the degenerate Hilbert space. And you have byproducts. So you're used to products as being a product where you can project from there onto each factor. There's also something called a co-product where you can inject from either factor in. And you usually get in sets, for example, you just get the direct sum of two sets. You can inject each in there, and that's the least thing you could do with them without overlapping. It turns out in Hilbert spaces, the two agree. You try to form a Hilbert space, take a Hilbert space H and a Hilbert space K, and form the smallest Hilbert space you can generate from the two of them. It's really the product Hilbert space. Okay? I don't know if you'd ever thought about that, but that's what's called a byproduct in a category. And it turns out this category is what's called dagger compact closed. So you can always take for any linear space its dual space. Those are the continuous functionals into the complex numbers in our case. And you can actually extend that to a mapping on morphisms, such that if you take the dual of the dual, you get something isomorphic to H. And if you take the corresponding dual of the dual of F, you get F back again. And this dagger here is the adjoint that you're used to using. Okay, and it has a nice property like this. So there's an interplay between the usual functional analysis dual and the adjoint of Hilbert spaces. Okay? And these categories that satisfy these properties, and you can state them completely abstractly, are called dagger compact closed. And there's a theorem or results. I guess it's not a theorem, I think. But anyway, what Abramsky and Bob Koka proved was that dagger compact closed symmetric monoidal categories with byproducts model the finitary quantum mechanics in a very strong way. You can prove in this setting things that you can prove in the Hilbert space formalism and vice versa. It turns out for the justification for the logical stuff I was telling you, there are also models of multiplicative linear logic, which is one of the fragments of linear logic. So that's the tie-in with why I asked you to think about linear logic. And it turns out an abstract setting in which to reason precisely about quantum protocols such as teleportation and entanglement swapping. In their paper on this in 2004, I think, they showed how to use this approach to prove that teleportation works, or that entanglement swapping works. They gave proofs of these. And reasoning about resources at a level that usually aren't dealt with in the Hilbert space formalism, kind of surprising me. It turns out that their work and that of Peter Selinger devised what's called a diagrammatic calculus for reasoning about systems in this approach. Bob Koka has been talking about this lots. Here's an example of teleportation where you have the state phi that you want to send from A to B. Here's Alice and here's Bob. And you have this bell system here where you then have this entangled pair and this gets sent through there. And you send over 2 classical bits, and then Bob can apply the appropriate measurement to get the state phi out on his end. Okay? And so time here is meant to flow from bottom to top. That's just a picture. But you can use these diagrammatic approaches, these diagrammatic reasoning, string diagrams is what they're called, to reason precisely in this rendering, in this representation. It's very nice. There are 2 issues here. One is you have a certain family, certain categories that work to model quantum mechanics, okay? So you're substituting the Hilbert space formalism. For that, you're going to substitute reasoning in category theory. And if you've ever done any category theory, you realize that's always big diagram chases, and they can get quite complicated and so on. The second point is, well, no, in fact, there is this, at least at the local level, very simple diagrammatic calculus you can use to reason about them. You don't have to do the Hilbert space formalism. You don't with the Bras and the Ketz and so on. You don't have to do the diagram chases that usually accompany category theory reason. You can, in fact, use these this string diagram calculus to reason about things, to prove things in this world. So this is really an important thing to know about. Okay? Yeah.
Has the diagrammatic calculus been extended to open quantum systems, where here you're using pure states, unitaries, projective measurements,
Right.
and rather we would use density operators, channels, and
I'm not an expert on that, so but I suspect yes. There's Koka and Kissinger have a book called Picturing.
quantum pictorialism.
Yeah, and there I think you will see a definitive account of what's available now. Okay, so off into the swamp and now back. I started with a question initially about what's a prototypical quantum computer, and I dragged you through all this abstract mathematics. See how long it stayed with you. So we're back to this question about Nils QRAM model, where we had a classical computer on the left and a quantum coprocessor and this connection between them. So in the rendering I'd like to present then, I want to think of a quantum programming language as a functional language for programming the classical computer, a linear language for representing the quantum circuits I want to generate and run on my quantum coprocessor. And so this is sort of a connection between the two at the language level. Now the other thing I have to admit is at this level, we're going to elide measurements and simply address the question of a functional language for constructing circuits and a linear language for modeling them as linear morphisms, okay? But we're not going to have any notion of execution here. And so we won't have measurements. In fact, that's one of the things that we're going to be looking at going forward is how do you build measurements into this scheme so you actually have a notion of execution over here. And that's something called dynamic lifting. But this alone is the setting in which we can talk about programming languages for these machines. And we're going to describe these as circuit description languages. And they're prevalent not just in quantum computing, in fact, for classical computing. They want to have languages that describe circuits that they create for circuitry, electrical circuitry. And it's a very intricate system, area where you need these powerful languages to reason about things, because circuits, as you know, can be quite complicated. So we're going to model circuit description languages, what are called linear nonlinear models. So let me tell you a little bit about that. So again, here we're going to have a functional language on the left and a linear language on the right. This represents classical, this represents quantum circuits. And so a linear nonlinear model is this picture where over here, well, we said for functional languages, for classical languages, we need Cartesian closed categories. Over here, I'm going to have a symmetric monoidal category L for the linear part. And then I have these strange symbols. Well, this is a symmetric monoidal adjunction. So what's that? Well, I didn't tell you what functors are. If you have categories, then you have to have maps between them. And a map between two categories is called a functor. It takes objects in the category C to objects in L. It takes morphisms here to morphisms in L. And it's got to obey the obvious rules, that it takes the identity maps to the identity of the image, it obeys composition. And a monoidal adjunction, two functors, so G's a functor going back, that's often called the right adjoint or the rounding functor. And this forms an adjunction, means there's a close connection between these two functors that I don't want to get into the details of, but not just any pair get to do this. Okay, let me put it that way. And to say this is a symmetric monoidal says that F has to preserve products by sending products in the Cartesian closed category to tensor products in L. It's got to take sums in this Cartesian product space to sums in L. It's got to send the empty set. Well, that's the initial object here. The empty set, if you've ever thought about it, is the one set where there's a unique map into any set, the empty map. And that's it. It's the only map you can define. And that's the only set with that unique property. So this is what's called the initial object in C, and it goes to the zero object in L. And the terminal object in C, which we said you had to have, maps to the tensor unit in L. And now this operator we talked about, this of course operator, this bang operator that allows you to duplicate resources, in the linear category you want to represent that, and it turns out it's the composition of first taking this G back to C and then taking F back up to L. Okay, and that's how you can get it concretely in this setting. Okay, so you're trying to figure out how to relate these two, and that means describing how the bang operator of linear logic enters the picture, and this is telling you you need this. And it turns out the basic result was that these constructions, these symmetric monoidal adjunctions between a Cartesian closed category and a symmetric monoidal closed category L, these are exactly the models of intuitionistic linear logic. This is a result of Nick Benton in the mid-1990s. There was, if you recall, I said Girard first proposed this linear logic in the late 80s, 1987, and there was a big concern in the community, what are the models of this? And Benton more or less settled that in the mid-90s with this approach. But it's convenient for us because it says this is what we should be looking for as models for these prototypical programming languages that, for something like a QRAM model. Okay, so the language we used for the work that we've been doing is one devised by Peter Selinger and a student of his, Francisco Rios. And this is called Proto-Quipper-M. So you may have heard of Quipper. That's a language that Peter developed that's an embedded language in, embedded domain-specific language in Haskell. And as part of this project, Peter wanted to free himself from Haskell because it's just too big. There's no way you're going to do semantics for that because it keeps changing. So he wanted a setting where he could get his own, develop his own type system and build the semantics from the start. And one of the first languages he proposed was Proto-Quipper-M for model. And so it has these types. Most of them should look a bit familiar. These are linear now because I'm taking the linear morphisms. You have this bang modality here, and then you have something called a circuit. At the linear level, it should be thought of as a quantum circuit of type T arrow U. So it takes inputs of type T and outputs, it gives outputs of type U at the quantum level. Okay? There's also intuitionistic types, so they represent what the classical world looks like. And there you have this zero type sums, the identity for the product. We use the same product symbol here. Again, the bang modality is should be thought of as intuitionistic. And circ appears at this level as well. And then there are M types. So what's this about? Well, Peter's idea was, we know, for example, you can start with finite dimensional Hilbert spaces, and the linear maps there should represent quantum circuits, okay? So think of starting with some symmetric monoidal category like FD-Hilb and taking your morphisms from that. And then you're going to build a model using those as the representatives of what quantum circuits look like. Okay, so that's what the M types are. They're the basic circuits you're looking for, and there's alpha here. It's a certain family of them you might take as given to start with the tensor unit, and you can take a product of two. And then here are the terms, and again, you see this these constructors for dealing with all of the various types, and lift and force. We've seen box T. This is what you do when you have something that's a quantum circuit and you want to make it intuitionistic. So you can send it to the classical computer to manipulate. Can't open it up, it wants to treat it as a unit that it can pass around and maybe figure out how to build more complicated circuits from the simpler ones it's already built. So this box operator really says, I can take a circuit, a linear circuit, a quantum circuit, and send it over to the classical world and let the classical world use it as a tool to create new circuits. And then there's an application, and this is the what circuits in the linear world look like. They're really what you would think of as a quantum circuit C, but this is labeling the inputs and the outputs. So think of it as it's a circuit that takes in n qubits and outputs n plus m qubits, something of that nature, okay? That's what it's meant to have you think of. All the types other than these are linear. So even, for example, the arrow type is linear. Even if A and B are intuitionistic, this is still treated as linear. These, as I said, the M types are the morphisms from some fixed category you start with, like finite dimensional Hilbert space. And the other interesting thing here, which was meant to be a benefit for the programmer, was instead of having a type judgment for the classical part and a separate one for the linear part, Peter said, let's put it all into the linear world, and that's where we're going to operate. And so the programmer can live in that world. I'm not sure how much of an advantage it is, but it turns out mathematically, for some of the proofs, it turns out to make things work very nicely.
What's an example of circ TU? I mean, like, you said that you have a type T and then unitary.
You could take a Hadamard.
Okay, but what is the type for that?
Well, Hadamard takes in a qubit and outputs a qubit, so it's qubit.
Oh, I see, it's qubit to qubit.
Yeah.
So I should think of type as like
Type's telling you.
the number of qubits.
Yeah,
or the size.
yeah.
Okay, sorry.
Right. Right. No, this is. It's a good question at this point. If you want to try to keep your hands on reality, if reality is qubits, then it's nice to know. Okay. So here.
10 minutes.
Huh?
10 minutes.
10 minutes? Oh, okay.
Yeah,
That's more than
an extra few minutes.
Yeah, I'm probably not. This is taking longer than I thought, but I'll make the slides available. So for those of you who are interested, you read them. For those of you not, you can put them in the trash. Okay. So here, for example, you take a Hadamard. Take H as a constant representing the Hadamard gate. Then the 2 Hadamard says apply the Hadamard gate twice. Okay. That's just an example. So in this very complicated system, box Q is just telling you the input type of this. You lift this thing. Q has type qubit, HHQ. Okay, so that's applying the Hadamard gate 2 times. And this is, right here is just something that's a linear circuit, but you lift it to make it so you can have many copies of it. And now you box it up so you can send it over to the classical world, let the classical functional language use it. It's an intuitionistic term. It can be copied and deleted. So one of the things about Peter's approach is you want to be able to write circuits for any quantum computation you might think of. But some obvious ones are, for example, if you want to do Shor's algorithm, you want to have the quantum Fourier transform available. And when you think about it, you realize that, in fact, that's not just one circuit. It's a whole family of them, one for each size of input that you might be expecting. And so when you talk about this language, when you talk about building circuits, you really mean for each one you should have a whole family where when you come upon, you want to apply it in a particular setting to some input, you have to first be told what the dimension of the input size is, so you can appropriate the, you can use the appropriate circuit. You don't want to try to be generating that at runtime. You want to have the whole family there. And the thing to notice there is that n, that's an intuitionistic value, so you can pass that around and just use it. You don't have to worry about the, you know, the no cloning and the no discarding for that. Okay. So Proto-Quipper-M is used to describe families of morphisms, mappings, quantum circuits, that come out of a fixed symmetric monoidal category. Okay. So the model that Peter and Francisco presented was one where the functional language is modeled in just sets, and the linear language is modeled in this rather sort of bizarre construction, which is building a category on top of a category. So it's what's called a functor category. The idea was you start with, say, FD Hilb, and now you've got just some symmetric monoidal category. There isn't enough structure there. So you apply this operation to it, and that gives you a category that is closed, so it has an internal column in it. It also has all products that you could want. Okay, you can form any product you want. And that was needed, in their view, to do the modeling. So don't worry about what this is in detail. It's just a way to start with M and add some categorical structure you want. Okay? And then the theorem that they proved was that this simple categorical model is type safe. So what that means is if the program types, you won't have runtime errors. It's sound, so if you can prove structurally that a computation terminates, then in fact it will when you run it. And it's computationally adequate. That's a weak form of completeness. It just says that if it terminates, well, if it doesn't, well, all you're worried about is termination or not. Okay, so if you take soundness and computational adequacy together, they're just addressing the issue of making sure that something that should terminate according to your rules actually does in the model. All right. So what our work is, I'll tell you about this, and maybe, I know it's been quite a while, so I'll just tell you what we've been doing, and then I'll ask you for some questions if you want. So our latest work was to add recursive data structures, and I'll give you some examples of those in just a second. It turns out, I mean, you have recursion at the term level where you do recx.t. For example, if you want to do factorial, everybody knows you can do that by recursion, things like that. But you can also do recursive types, recursive data types, and I'll show you examples. And so the second part of our work has been to add those to the system. Having recursive terms does not give you recursive types automatically. You have to work at it. But it turns out if you can do recursive types, term recursion follows. And it turns out the main difficulty is in the categorical model. What you need to do is you need to make sure you can identify properly the intuitionistic recursive types so that you can copy and discard them. If it's linear, it's a list of qubits, you shouldn't be able to copy or discard it, okay? But if it's a list of natural numbers, that's intuitionistic. You should be able to copy and discard those. So in the model, you need to figure out a way to distinguish those. And what we really wanted to do was design what's called the linear nonlinear fixed point calculus, which was a classical construction that was studied by Fiore and Plotkin. So here's the syntax. You have type variables, and now you see you have a type variable here, and the usual things, and then a recursive term. And same thing at the intuitionist for the intuitionistic types, and the other types have stayed the same. So here's some useful examples of recursive data types. The natural numbers are nothing more than recursing on 1 plus x, I plus x, where I is the tensor unit. And you can create a list of natural numbers by recursing on this. That's how you generate lists. If you want a list of qubits, you can generate, instead of tensoring with that, tensor with qubits. And you can actually do streams. So streams are like lists that never end. You just have an input. So a stream is like an infinite list where you have the first term and then the rest. And that rest means it never stops. And so here's a formula for generating those. And you can do a stream of natural numbers where now you see I have to use this of course operator, this bang operator, to be able to do these streams of natural numbers that never exist, that never terminate. Okay, so at this point, to talk about this, I have to get into complete partial orders. That's where recursion arises. And I think I've strained your patience enough already. You have to add more structure in the form of the types of categories you're looking at to solve these kind of equations. Each of these is what's called a domain equation. And complete partial orders, which stemmed from Dana Scott's work, exactly the area you want to look at to be able to solve equations like this, get isomorphisms like this in your calculus, in your model. Okay? I'm going to stop here before we get into the really difficult weeds.
Thank you.
So thank you.